I'm Neal Blair, and I'm a professor at Northwestern University in the departments of Civil Environmental Engineering and Earth and Planetary Sciences. And my specialty is the carbon cycle in surface environments.
That's really cool. And then how did you get interested in research in the first place?
It's kind of a gradual process, at least for me. When I was in elementary school, I was exposed to another student brought in a jar of frog eggs, and we watched them hatch over the coming weeks and then start to develop legs and become small frogs and stuff. And that totally changed my outlook. I was living in the country, so my family was very rural, lots of farms around. But for me, being outside, it was always a very functional thing in that either I had tasks or jobs to do, or my mom was kicking me out of the house just to be out of her way and I had to be outside. But I never thought about the natural environment much until I saw that example. And that caused me to start looking at things more. And I just fell in love with being by streams. We lived near a stream, and I just loved being by a stream and looking for things like that. And I realized I actually started doing research then, but I didn't know it was research, in that I was being an observationalist. I was trying to understand what was living in the stream. What could I find? And I start setting up little terrariums and aquariums in the house and bringing back things from the stream and watching them there. And then I think my next real research activity came in high school when I was taking chemistry. And I found that I was really good at chemistry. I don't know why, but I was just felt natural with it. And again, another friend, a classmate, had brought in this old book that he had found someplace. It was a really, really old chemistry book on how you do elemental analyses before there were instruments. So it was like a whole flow chart of if it dissolves in this, but doesn't dissolve in this, but then dissolves in that, it must be whatever. And it was like how the 1800s chemists would figure out things. And he was interested in it because it was kind of like an old book. And I was going, well, that's kind of cool, because at the same time, my dad had been asked to consult down at the Baltimore Harbor. So I grew up in Maryland. So his ship came in, there it is, full of this stuff. And it bamboozled everybody at the harbor. They didn't know how to get it out of the ship because it wasn't magnetic. So the way they always moved metal ores, which were mostly iron ores, was to use a big magnet and pick it up and move it from the ship into trucks and stuff. And this stuff was not magnetic. And it's basically what chromium is extracted from. And so he brought home a handful of this stuff and just gave it to me. My dad would do that occasionally. He would just give me things that he thought were kind of unusual. He had no intent, as far as I could tell, for me to do anything with it. And so I just brought it into school, and my friend Wally and I used this ancient book to analyze this rock to figure out what metals were in it. And so that was kind of like my next research project. But what's the take home message here is everything was play to me. It wasn't like, oh, I want to do research. It was like, oh, here's something kind of cool, and I'm going to play with it and see what I can learn. And that's what research has always been about to me. Now, it may be different for different people, but it's always been, I mean, just like some people would do sports and other people may play piano or something for fun. It's something that you felt good doing. And I didn't call it research, but it was just my playing around with things. So that's a long answer, but in a way that's something to think about at your stage is, yes, there may be a tendency to want to formalize research. And that's always a good thing eventually, because there's a process to doing scientific research. But I think if you're not ready to play with it on your own, then you might want to wonder, should I be doing research? Because it's not for everybody.
Yeah, okay. And like the chromium story was really cool. In understandable terms to a high schooler, could you give me an overview of your research?
Let me just back up and say that I ended up getting a chemistry degree as an undergraduate and then got my PhD in chemistry, mostly in organic chemistry. Not because I was in love with chemistry for chemistry's sake, but because I saw that chemistry would be a really valuable tool to study the outside, the environment. And I found that one of the things I was just kept coming back to was I like being outside and looking at things. And so being able to do chemistry was like having another set of eyes. It was a set of sensors that gave me a new way to do things rather than just touching and looking and smelling. Okay, so that's sort of the background. And so I kind of thought looking at how carbon behaves in the environment always appealed to me because carbon is so central to life. All life is based on carbon that we know of. And there's just so much information in carbon. If you think about all the different forms, all the different compounds carbon can be in. So carbon's really unusual if you think about it because of the way it bonds. And you have this whole field of organic chemistry where if you think about how many organic compounds are there, I don't think we know. I mean, thousands probably. But if you think about any other element, no other element has as many different compounds that can be made from it as carbon. And so to me and to people in my field, that is actually information. It's like you have a much bigger vocabulary to look at the world with when you're looking at carbon. It's like you have almost infinite numbers of words you can make. If every molecule is a word, just think about how many words. Whereas if you think about iron, there's only a few words you can make with that. There's iron oxides and reduced iron pyrite. We could list 20, 30 maybe iron compounds, and then we're done. I kind of saw the power of that very early on, that carbon came from biochemistry. Biochemistry is such an important thing on the planet in terms of shaping the chemistry of the surface of the earth. So I really look at how carbon behaves and what form you find carbon in surface environments like soil and sediments. So I actually got started doing oceanography, looking at carbon cycling in the ocean. And then when I moved to the Midwest, I was working in California and then North Carolina. And then I moved to the Midwest and started looking at more on soils, since that's what we have a lot of around here. But my big research project now that's been going on for several decades is how have humans influenced the carbon cycle by land use? Okay, so for instance, if we're doing agriculture, which is changing a natural ecosystem to an anthropogenic ecosystem, is there impact on how the carbon cycle behaves? And it turns out everybody agrees yes, there's a big impact, but we don't agree on how and what it is. In other words, some people have said, oh, when you till a field, for instance, you plow a field up, you release a lot more carbon into the atmosphere. And so that's adding to all the CO2 that we're putting in with fossil fuels, which is not good. However, there are other people who have done sort of global models that say, oh, when you do all this, the net result is you pull more CO2 out of the atmosphere. And so that's actually potentially a positive thing. What I take away from that is that we don't know. My lab is actively doing lots of experiments to try to figure out which way does it go. In fact, I think what we're discovering is, yes, it goes and it comes. And depending on where you are, it may be one way or the other, or when you are. So we think it's time dependent and place dependent. And figuring out what the net result is over the whole planet could probably be beyond my lifetime, because I think it's a very complicated problem, which is exactly the kind of research project you want, because it will keep you busy for a long time.
That's super interesting. And then, what's one of the biggest challenges that you faced in research, and how did you overcome it?
You're always encountering challenges because if you're doing research correctly, usually you're wrong half or most of the time. The way we teach people to do research is you develop a hypothesis. I personally don't feel that you have to have a rigorous hypothesis. Sometimes you just have to go look at things because you don't know enough to make a good hypothesis. But let's suppose you have a hypothesis, or at least you come into a setting where you think you know how things are going to work, and you're doing an experiment to confirm it. Half the time, you find out, oh, things aren't working like you thought. And depending on how much investment of effort and time you've put into getting to that point, that can be a hugely demoralizing situation to be in because suddenly you realize that you don't understand the system. You've now just invested a year, 2 years, 5 years, half your career sometimes on getting to that point, and then you realize I don't understand it. And that to be a really good researcher, you have to be able to pick yourself up at that point and say, okay, maybe I'm about to discover something really exciting and I think I can figure this out, but I just need to give it some time and effort. And I think if you're going to survive being a researcher, you have to train yourself to have enough confidence in yourself to be able to get over those hurdles because you will encounter them over and over and over again. It's hardest the first time when I was working on my PhD because everything counts on being able to get it done. And that's the first time you're really doing serious research. That's the toughest time because you've not had to deal with it before. And I've seen some people just get beat by it and then other people figure things out.
And then, in contrast to the last question, what do you enjoy most about your research?
I think discovering something that no one else has seen, when you suddenly make a measurement or you get a result and you go, oh my God, no one has ever seen this before, and you believe it. I mean, sometimes you find something that no one else has seen before because you screwed up. You need to be a little patient with yourself and test to make sure it's right. You have your quality assurance. I tell my students QA, QC, quality assurance, quality control is anytime you see something new, take a step back and let's start testing to make sure it's right. But once you get to that point, you feel confident that you've discovered something that's really novel. There's no feeling like it. It's almost like being the first on another planet or something. It's like, oh my God, I'm the first one here.
And then, which person or mentor in your field has made the biggest impact on you?
I think that's an impossible question to answer because there have been so many people. I can start with my friend Walter in first grade, who brought in the frog eggs, who totally changed my outlook of the world. And he was kind of a mentor. I don't think either one of us understood that. I had a very good chemistry teacher in high school who allowed me to go back into the back room, the prep room for the chemistry lab, and play with micromite with Wally. My first official research was done in college at the University of Maryland with a professor named Dr. Panamaruma on Arja life studies. And so that was really important to me because I got to get exposed to what professional researchers did and worked with grad students and professors on that. And then my PhD advisor, Dr. Bonner, was hugely important, as well as my postdoc advisor. I went to NASA, I worked in extraterrestrial research for a while. My postdoc advisor, Dr. Demaray there, was really important. So every step of the way, there's always been someone important. It never ends.
Yeah, okay. And then, where do you see your research field expanding to? And like, what are some interesting topics that can be further explored within the next 10 years?
It's unimaginable what all the topics are that's going to be. I mean, the next 10 years, it's just clearly things that we need. From my perspective, from the carbon cycle, we have to get much better at sequestering carbon, at pulling carbon out of the atmosphere. That's a technology that people are working on, and we have ways of doing it, but it's not terribly energy efficient at this point. And so we need people who can work on that. Prediction, whether it's environmental prediction or other types of prediction, is going to be really important. And this is where AI is probably going to turn out to be hugely important. And so there's room for computer scientists, new materials being designed for energy production and storage is another big area. Of course, there's always biomedical stuff. The things we saw with the COVID vaccine technology, the biomedical field is just going to take off in a very big way, particularly with AI. You could keep going on and on. I think every skill that is out there will see enhancement and a need out there.
Yeah, okay. And then, where did you start your journey through research? So, like, what were some basic lab positions or internships that you had?
I would start in college in that I started out doing research in professor's lab. And so that was sort of like type of course, you could get credit for it and stuff. And most colleges have that capability. And so that was where I really started doing research in a formal way. I don't think I was actually, well, I might have been paid during the summer, but I wasn't doing it for pay. And then my postdoc, after I got my PhD, I also taught, it wasn't research, but it was kind of related. I taught chemistry in the summer when I was a postdoc back at my grad school. I went to Stanford. And so they needed chemistry teachers. So I sort of did that on the side, but that kind of helped add to my ability to do research. And then I went straight from my postdoc into being a professor. So I was kind of on the straight and narrow in terms of employment.
And then how did you find your passion for research, and how would you suggest a high schooler try to find their own passion for research?
Well, like I said, going back to my original answer, to me, my passion was I liked playing with it. Discovering something you didn't know on your own as opposed to reading it in a book. I think that's the biggest difference between research and just education in general is in classes and everything, everybody's just giving you the information. And it may or may not have much context to it, and it may not have much meaning to it. Sometimes you just learn things because you know you have to learn them. And I think fundamentally the difference with research is you're finding out your own information about something that you're kind of excited about. And it could be you're finding out the information by going into the library and looking up stuff. That's research. Or you're taking a rock into the lab and dissolving it and doing some reactions on it. That's research. Or you're just observing things. You're going out and looking at what kind of birds you can find out in your neighborhood. That's actually research. People do that. And so I think that's the fundamental difference is you like going out and collecting your own information so that you've learned something. Not everybody likes doing that. I've seen most people, I don't know how many thousands of students I've taught over the years. And I would say only a small fraction do I see the researcher in them. No, most of them are just, I want to get this done. I take the test and get done with it and move on. And I just want to get my job. And so I can do things on weekends or whatever, or I can afford a nice house or a car. I mean, a lot of people are just like that. But every once in a while, you run across someone who just goes, I need to learn more about this. And that's a researcher. So I think you as an individual need to ask yourself of that is take a step back and ask, what does it mean to you? Because it's a deeply personal thing. If you view it as a job or you view it as a way of getting rich, whatever, then probably aren't going to stick with it all that long. It's not going to be sustainable. But if you view it as kind of like a passion or a plaything, then I bet you're going to be a researcher long after you get out of school. That's basically what happens is school never ends when you're a researcher.
And then what kind of skills do you think a high schooler could develop even if they don't have access to a wet lab or any of the tools that you guys have?
Any skill. So to be a researcher, you need to be good at something. So you could be good at math. There's a ton of math research going on, not just as math, but in all sorts of fields. So in my field, for instance, we have people who are really good at going out in the field and working there and using the landscape or the ocean as the laboratory. And that's a skill set. Not everybody can do that. And then there's some of us like me, I'm really good in the lab. You give me a rock or some sediment and I can tell you what's in it. Okay. And that's valuable. I've got friends who are really good. All they can do is math. I would never want them in the lab. They're a disaster. They break everything, but they're math geniuses or they're really good coders. And we need those people because I can't do those things. And so some of my problems get so big and so complex. I need someone who can deal with the computer side of things or the computational side of things. So just in my research alone, I have friends, I have collaborators. Researching is not a solitary endeavor. It can be, but it's not as fun as if you can do it with other people. And so like the current research I'm doing, trying to understand how land use influences the carbon cycle. We have 5 universities involved. We have soil scientists, we have sediment people, we have ecologists, we have people who do atmospheric stuff. We have people who are lab people, field people, and people who are really good with calculational things. We have engineers. We have people who do remote sensing. We have people who do everything just to solve our problem. And so you don't need a wet lab. You don't need a dry lab. If you got a brain, you can do research. That's the beauty of it. So my recommendation to anyone is find something that you're kind of good at, whether it's chemistry or physics or math. It doesn't even have to be science. It could be social studies of some sort, because those people are needed too, because everything involves people. But like our study is how are people influencing the carbon cycle? So we need the people element too, psychologists and the whole bit. We've even had artists come in and say, how could you use art to describe what we're doing so that your average citizen, your average person might better appreciate what we're doing? Because the average person is not going to understand the chemistry. If they're not a scientist, they're not going to understand the science. But if you had a poet or an artist or a musician come and somehow describe in their own vocabulary what we're doing, then you may reach people out there and educate them in ways that a scientist couldn't do. In fact, some people won't even listen to us because we're scientists, because it's too hard. So get good at something and then find a way to use it.
Yeah, okay. And then what traits do you think define a great researcher in their field? And what type of traits would you look for in a potential lab member or collaborator?
I've already given you some clues. I'm very interested in someone who's a good observationalist. In other words, do they notice things? One of my best mentors like to talk about this a lot. He could look at you and tell you all sorts of, he was a great profiler. He was a chemist, a geochemist, but he would look at you and tell you all about your family and stuff after talking with you. But he was great in the field too. He would love to go scuba diving or go down in submersibles or go anywhere because he could look around the environment and tell you how it works. So I've always felt strongly I want people who notice things, and I want someone who brings in a skill set. And for my group, I like to get people who bring in skill sets that we don't have in the lab. So I'm a chemist. And I'm happy to have other chemists in the lab, but I've actually had more biologists and geologists and other types come in the lab than chemists because they can bring something to the lab that I don't have. Someone who's stuck with things and developed a talent, and someone who notices things around them. They're not just burrowed into some little rabbit hole and never look up. That's never good.
And then just for our final question, what's some advice that you would give to a high schooler who wants to go into research?
Learn to problem solve. I think I got lucky. I should have mentioned one of the most important mentors I ever had was my dad, in that he was a farm equipment mechanic. I think he only went through 11 grades, so he never went to college, never went to 12th grade. And he would often take me on repair jobs and things, which I always thought were horribly boring when I was a kid. Hand me this tool, hand me that tool. All the while he was training me, I didn't realize it to know which tools did what. What I took away from that was he was always running into problems. When you're trying to fix something that's broken, you have a problem by definition, and you don't necessarily know what it is. In fact, typically you don't. And so there would be times where I would just look at it and I go, how did you figure out how to solve this problem? He'd always say, it's Yankee ingenuity. And I remember thinking as a kid, I don't know what that is, but I need to get some. But really what it is sticking with a problem, tearing it apart and working on it, never giving up until you solve it. And I think being in that environment as a kid, I'm now 71 years old. And so looking back over 60 years of this, of my life since then, I realized that that is the single most important trait that I probably developed. What I learned over my years is don't be afraid of problems. Don't be afraid of breaking things. Don't be afraid of being wrong, because you'll be wrong more times than you're right, but you only need to get it right once, and then you've solved the problem. Start now. And I don't mean just math problems your teachers give you. That's part of why they give you these things. They never explain why you do that, but that's really what they're trying to get you in the education system, is to get you to figure out how to fight your way out of a paper bag, basically. It's much more fun to do it outside of a class.
So that's all the questions that I have for today. And thank you so much for meeting with me. I really enjoyed talking to you.
Same here, and good luck.